Hi, my name's Peter, I'm here today to discuss the action potential. So first, what is an action potential? Well, an action potential is going to be a change of voltage within a cell that acts as a signal for rapid cell communication. So this is a response to a stimulus. So something's going to happen. It's going to trigger a rapid change in the voltage of the cell, and then this signal will signal to other cells, and trigger a response. This is a really good method of cell communication because we know that electrical signals will travel faster than chemical signals, right? If we have an electrical signal, it's going to very rapidly travel over distance faster than, let's say, a molecule could travel through a bloodstream or something. So what exactly is happening here? This is a diagram showing us an action potential occurring, but what exactly is this? So this diagram is going to show the change in membrane potential at a specific point over time when an action potential occurs. So this is going to be our time. As we progress through the action potential, this is when an action potential occurs, and we can see our voltage is going to rapidly get very high and then rapidly get very negative and kind of even back out. Important thing to note is that the magnitude of this change is going to be constant, right? So we can change the frequency at which these occur. There can be a lot of action potentials, but we know that the change in voltage is going to be the same every time. So let's get into the actual steps of the action potential. Let's just go over this real quickly in the diagram so we can see that we start here at rest. Our rest is roughly -70 millivolts, and this red line is going to represent the membrane potential, or the charge, the voltage inside the cell as we go through our action potential. So we can see that this is where our stimulus occurs. It triggers an action potential. This is going to be the threshold. If the charge reaches this threshold, it will trigger an action potential, which will trigger a rapid rise in the membrane voltage. It's going to depolarize, get very, very positive, reach this peak, and then it's going to go back down and get very, very negative. It's going to hyperpolarize, and then it's going to return to rest. So first, before an action potential even occurs, our cell starts at rest. The membrane potential at this point is going to be very negative. And the reason for this is because we have these two forces acting on our cell and nothing else is occurring. So we have this sodium-potassium pump. This is going to do two things. It's going to pump sodium ions outside of the cell, and it's going to pump potassium ions into the cell. So this is going to cause the outside of our cell to become more concentrated with sodium ions, and the inside of our cell to become more concentrated with potassium ions. The rate at which this occurs, the sodium is actually pumped a little bit faster than potassium ions, so we're already kind of evening out our charges by pushing more positive ions outside the cell, which is making the inside of the cell more negative. Another thing that's contributing to our resting is this potassium leak channel. Potassium ions are going to go out of the cell. Positive ions exit the cell because these potassium want to go from high concentration to low concentration. Positive ions go out. Our cell is going to get a little bit more negative inside. Okay, and then what's going to happen once our stimulus reaches our cell? Well, it's going to be the rising phase. So something's going to happen outside of the cell. It causes it to become just a little bit more positive, right? So we reach this threshold, and what this threshold is the voltage required to open our voltage-gated sodium channels. These sodium channels are specific to sodium ions. They will open when the cell depolarizes slightly, and they're going to open, and since our concentration of sodium ions outside the cell is so high, the sodium ions are going to rush into the cell, and it's going to rapidly depolarize, become more positive, and we're going to reach this step, which is going to be the peak of our action potential. At this point, the concentration of our sodium ions are going to start to even out. As we can see, the rate at which these sodium ions are traveling through the sodium channel, voltage-gated sodium channel, is starting to slow. And the cell's becoming very positive because we have so many positive ions inside the cell. Around this point, after a slight time delay, our voltage-gated potassium channels are going to open. Now these, if you'll recall, when we're at rest, we have a lot more potassium ions inside the cell. Because we have so many potassium ions inside the cell, and because the charge is so positive, our positive potassium cells are going to rapidly rush out as soon as these voltage-gated potassium channels open. And as you can see, the membrane voltage is going to rapidly fall. It's going to actually overshoot resting, become hyperpolarized, very negative, And then finally, we're going to have our repolarizing phase where the membrane potential is going to be reset back to resting by the voltage. We're going to have all our voltage gated channels closing, but the leak potassium channels are going to start to return us to rest, as well as sodium potassium pump. And that is the action potential.